So what we want to start talking about today is how we extend ourselves into this multi-electron type system. So if you remember last time, we did a bunch of stuff with term symbols, and pretty much everything we were doing with the term symbols was talking about the spin and the angular parts. So if we look at this type of situation where now we want to say, okay, well, we did like a P2, we were looking at two electrons, and we were just looking at that spin-orbit coupling, the spin and the orbital angular momentum. What do we do about the radial part and the motion part? So we've got our motion of the first electron, motion of the second electron, attraction of the first electron to the nucleus, attraction of the second electron to the nucleus, and then the repulsion of the two electrons, which is going to depend on this distance between the two electrons. And what's nice to do is to recognize that we can kind of see this. If we look closely, we can see that this part is just like a hydrogen atom that just depends, a hydrogen Hamiltonian that just depends on the R1 components. So this del squared 1 would be for R1 theta 1 phi 1, just dependent on this electron moving around in three-dimensional space. And then our attraction is just an R1 term. Same thing here. We've got some H2 that also looks like a hydrogen atom with some R2 theta 2 phi 2, some R2 attraction. And then we've got this unfortunate part at the end. This unfortunate part at the end can't really be simplified anymore. So this is going to be plus E squared over 4 pi epsilon naught 1 over R1. And we usually abbreviate this absolute value of R1 minus R2 to just R12. So the distance between the two electrons, which is another variable that depends on the two positions of the electrons. And the trick we've always used in the past is we've always said, I can take this part that's got my R theta phi in terms of R1 theta phi, theta 1 phi 1, and this part R1 theta 1 phi, or R2 theta 2 phi 2, and I can treat them separately. Separation of variables. We did that on the first day of class kind of quickly when we were splitting out time. We did that again when we were doing the multi-dimensional particle in a box, 2D particle in a box, or 3D particle in a box. We saw separation of variables again there. That's what made it so it solved nicely. We saw that when we were doing our rigid rotor and separating our orbital, separating our rotation versus our tilt. And then we saw it again in the hydrogen atom where we were able to separate R theta and phi. However, when we look at this term, this 1 over R1, R2 absolute value, there's actually no way to simplify this. We can't use separation of variables. This is going to create some problems for us in terms of what we're able to do. Now, we can still kind of make a first pass at what we think a good wave function would look like. So we can say, we can guess at some wave function that's going to have some like R1, theta 1, phi 1, R2, theta 2, phi 2, right? So we are in 6 dimensions now, right? We're at 6 coordinates. And we can kind of say this is going to be some, and actually, it actually should be more because I don't have my spin components in there. So I'm going to toss in the spin components for fun as well. We should also have that sigma 1, sigma 2, our spin variables. No classical analogy, but we should also include our spin parts. This would give us some function some psi n l m sub l, which we'll just say depends on like an R1 vector, times some psi n l m sub l that depends on an R2 vector. And I'm actually going to put little primes on these because these N's and L's don't have to be the same. They can be different things. This would essentially give me one function that's related to this part of the Hamiltonian, another function that's related to this part of the Hamiltonian, but it completely ignores that repulsion term, this electron correlation term, the way that the electrons interact with each other. This is still going to give us some sense of how we can start to get solutions. And you notice we're getting solutions that are in some regard related to the individual parts that we can see. We can also see that if I expanded this in terms of the r, y, and sigma, that we're going to have like a spin orbit part. And when I look at this, the Hamiltonian that's up here, it's really the radial part that's going to matter more. So the stuff we did last time with term symbols kind of took care of a lot of the issues with the theta and phi and sigma part. And the part we're going to look at today is going to start getting us to think about the radius part. Part of the reason we're able to do that is because the spin-orbit coupling term is on the order of 1,000. It's 1,000 times less than these other parts. So often we can neglect it and just bring it in later as like a small correction. So I have a note in my notes that says entering approximation land. We are out of problems that we can exactly solve. So at this point, we need approximations. So we're going to use two main approximation methods. I'm hoping we'll get to talk about one of them by the end of class today. One of them is going to be perturbation theory. Which I liked for lots of years. Perturbation theory is really handy when you're doing stuff in nuclear magnetic resonance. But then we're also going to use parameters. Did I spell that right? Variation of parameters. And variation of parameters is actually a really powerful method. Both of them are going to require us to have some kind of good guess at where we're going to start. So this type of wave function that's looking at how, the attraction to the nucleus could look like two hydrogen-like wave functions multiplied together, that's going to be our good guessing start for both perturbation theory and variation of parameters. We're going to see that there's some other manipulations we can do, some other ways we can think about all of that. But first, we've got to talk about what makes a good wave function and what makes a bad wave function. And particularly, we're finally going to derive the Pauli principle. So this is not the Pauli exclusion principle. This is just the Pauli principle. It is sometimes referred to as the sixth postulate of quantum mechanics. And what it says is, wave functions for electrons must be antisymmetric. We will see later on why that becomes really handy in just a little bit here. And we'll also see how this leads to the exclusion principle, which makes it so we can't have two electrons with the same set of quantum numbers, how that restricts our allowed quantum numbers. Essentially what this means is if I have a wave function that depends on some R1 and some R2, again, looking at all of those possible R theta phi's, R theta phi sigmas, R theta phi sigmas, and I switch R1 and R2, so I've got R2 and R1, I better get a negative sign up front. Now, maybe you can see it just from this, but essentially what this does is it guarantees, if I just move this over and say psi R1, R2 minus plus, ooh, no, that doesn't work. So what we're going to see is this is going to give rise to a couple restrictions on our wave functions. And the first thing we have to realize, in terms of the different types of functions we can write down, is I can write down some wave functions. If I'm looking at my n, l, m sub l, and I want to come up with shorthand to represent that, I could say that this is going to be some, let's see, what's the best way to do this? Let's do it this way. Let's say we've got some psi of r1, theta 1, phi 1, sigma 1 is equal to, and I got some n, l, m sub l on there. We're going to use a shorthand where I could just say this is 1s alpha 1. So, yes, question.
I can't read the...
That's n, l, m sub l, this little subscript. So this is essentially specifying the fact that we've got some n, l, and m sub l, right? Same thing I had up here. So this is essentially saying I'm going to have my electron associated with my first set of coordinates, and I'm going to define the n and l right here in the notation we use in our Gen Chem class and the notation we talked about at the beginning of term symbols, but last Tuesday. And then the alpha is giving us that spin part, so this is specifically a spin up. And if I wanted to imagine, I could write a second equation. I could write a second one, some psi n, l, m sub l. I'll write it a little bit bigger. I didn't forget this time. R2, theta 2, phi 2, sigma 2 equal to 1s beta 2. Right, this is just going to simplify the way that we're writing things down and all of the stuff we're trying to represent. So, right, I could write this as like a 1s alpha, 1s beta, 2s alpha, 2s beta, 2p alpha, 2p beta, all of the different s's and p's to define those n and l's. And what we have to realize is if I want to represent two electrons, I have to represent both of these as products. So I'm going to put this together, and I'm going to say one of my choices for my wave functions, if I put these two together, would be 1s alpha 1, 1s beta 2. And then I have another choice. Because I really can't tell electrons apart, I have another choice where I could also do 1s beta 1, 1s alpha 2. I can switch that alpha and beta label. Now, we have more and more options we could do, right? We could bring in the p orbitals and the d orbitals and a bunch of other different wave functions to represent this. But given that we've only got 2 electrons, this is a good starting spot. This is a good place to start. Unfortunately, if you look at both what I have for psi 1 and psi 2, neither of them are antisymmetric. If I switch these, I'm going to get the same thing. So neither is I'm just going to put antisymmetric. Neither of these are antisymmetric. So they aren't going to follow the Pauli principle and be good wave functions. But because the electrons are indistinguishable, this idea that I really can't tell the difference between psi 1 and psi 2 just by mixing it up, I can also take linear combinations of them. I could take psi 1 plus psi 2, or I could take psi 1 minus psi 2. And that would also be a good kind of starting point. We saw that in a couple different places when we went back and we first did the particle in a box. We said we could have e to the minus ikx, we could have e to the plus ikx, and we could add those together to make an answer. So we can do the same thing here. But we're going to see, again, we only get one that's actually going to be antisymmetric. And this will give us the reason why anti-symmetry is actually important. So we could have psi plus, which I'm writing wrong already. Psi plus, which is going to be 1s alpha 1, 1s beta 2, plus 1s alpha 2, 1s beta 1. Or I could have psi minus. So it's just what I labeled as psi 1 plus psi 2, and I just switched where my alphas and betas were just because I like keeping my alphas in the same spot. And then I could also do psi 1 minus psi 2. So I can do 1s alpha 1, 1s beta 2, plus 1s alpha 2. Oh, sorry, minus there. It's very important. 1s alpha 2, 1s beta 1. And again, the reason we're doing this is a couple different things, just so we don't lose the train of thought. We're trying to find something that's a good starting point for solving this problem, even though we've got this thing that's going to mess us up. We've got an idea of doing a multiplication of two wave functions. We said we've got two wave functions we can write down. The problem is we also have this principle, the Pauli principle, which says they have to be anti-symmetric wave functions. And the Pauli principle is really similar to electron spin, or electron mass, or charge, or nuclear charge. It's one of those things that we're just like, there it is. There's a lot of interesting questions we could ask about it. There's actually a lot of interesting things we can do. Notice I say for electrons, it's actually for all fermions, which is, you know, a subset of particles inside of physics, which we're kind of doing as well. And we've also got bosons. Bosons don't have this restriction, which makes it so you can do really interesting things with bosons. But we're sticking with fermions. We're talking about electrons. And in order to have this kind of physical property realized, we're putting out some ideas. And I hope you can see if I flipped my 1s and my 2s, my psi plus would not be any different. This would be symmetric. But in my psi minus case, if I flip my 1s and my 2s, I would bring that negative sign out front. So this one is anti-symmetric. This is the one that we want for a good starting spot. Now, the reason that's a good one, and the reason that the Pauli principle, one way to kind of give a classical analogy to the Pauli principle is in the situation that remember the 1 represents the r theta phi for particle 1, the 2 represents r theta phi for particle 2. In the event that the two electrons go to the same spot in space, their r thetas and phis are equal to each other, psi plus would still have a value associated with it. Psi minus would not. So what that essentially does is it makes it so you've got, if you have the two electrons in the same spot, you're going to end up with a 0 probability for that to happen. This makes it so you can't have two electrons existing in the same spot in space. And since they're fermions, they're not allowed to exist in the same spot in space. This guarantees that my electrons are not going to have a probability of existing in the same space. And that's really what the Pauli principle gets us, is this guarantee that we're not going to have two electrons in the same place in space. So this would be our wave function for something like helium or lithium plus, right? Something that's only got two electrons. And this would be our starting spot for now thinking about how we're going to do perturbation theory or variation of parameters. We could start with a function like this and make some tweaks. Before we do that, let's kind of generalize this. Let's get a little bit broader. And let's imagine, what do we do for 3 electrons? Okay. 3 electrons. First off, the Hamiltonian would have another blue square here for another motion and attraction. And then I would actually end up with 2 correlation terms, because each electron is correlated to 2 other things. So I'd end up with 2 more terms out here. So I'd end up with 4 extra terms with just 1 more electron. But in terms of the wave function, whew, it gets a little bit more complicated. So if we're thinking about 3, I can imagine that I'm going to have a 1s alpha 1, a 1s beta 2, and a 2s alpha 3. We'll talk about why we go to 2s in just a moment, but we're going to have these 3 things. And I've got to take these 3 things, I've got to multiply them together in different orientations, and I can change those 1, 2, 3s, so I can get a whole set of possible functions. And I'm actually going to end up with 6 options. I can have psi 1. So we're doing this is for the 3 electron case. This was for the 2 electron case. So I can have psi 1, 1s alpha 1, 1s beta 2, 2s alpha 3. I can have psi 2, which I'm going to just flip some labels. 1s alpha 1, 1s beta 3, 2s alpha 2. And you don't have to write all these down. We're going to have a different way that's going to make it easier to write it down. So if you're copying all this, you don't have to. If you want to, that's okay as well. Psi 3, psi 4. I'm going to go 1s alpha 2, 1s beta 1, 2s alpha 3. Psi 4 is 1s alpha 2, 1s beta 3, 2s alpha 1. Psi 5. And all I'm doing is I'm changing my labels around to kind of make the different possible wave functions. 1s alpha 3, and psi 6 is also going to look like this. 1s beta 2, 2s alpha 1, 1s alpha 3, 1s beta 1, 2s alpha 2. So all we've done is we've taken our 3 electrons that we want to consider, and we've said we can kind of just take them and we can change the 1, 2, 3. I can multiply them together. I can get all these options. Now here's the catch. Yes, question.
Are in a multiple electron case, are the electrons considered indistinguishable? Or?
Yes. Right, which is why we had to do all of these, right? Alpha 3 versus, so if you look at this alpha 3 case, all of these really look the same, and I'm just changing which one is labeled with which. So right now, with them being indistinguishable, none of these are antisymmetric. So now what we have to do, in this case where we only had like 2 plus minus options, plus or minus, it's kind of easy to find which one was antisymmetric. In this case, how many options do we have? I can do plus, minus, 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 plus, 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 minus, plus, minus, plus, minus. There's a lot of options, right? And to go through all of those possibilities, and figure out which ones are symmetric and which ones are antisymmetric is a bit of a headache. Fortunately, instead of doing that, we're going to use matrices. Because it turns out that if we organize this, we can guarantee antisymmetry by putting it into a matrix. So the matrix that we would end up doing and I always try to write my matrices when I'm trying to make my matrix. So I'm going to call this psi anti, because this is going to guarantee an antisymmetric wave function. I'm not going to go through the trouble of showing you how you get the normalization factor, but there's a normalization factor. We're going to just write down these things. And I always write my 1s alphas And then it's going to be a 1, a 2, and a 3. Then I do my 1s betas. And it's going to be a 1, and a 2, and a 3. And then I'm going to do my 2s alphas. So 1, and a 2, and a 3. And my lines are not very straight, but as long as this and this is the determinant. As long as this determinant is not 0, as long as we get something out of this determinant, we're going to get, this guarantees that we get an antisymmetric wave function. We can kind of see this a little bit easier in the two case. Quick check. 1 through 5, taking determinants. Okay, we better take a determinant. Or 2. So, was it like you used to know and it's just been a while? Okay, so maybe if I do this reminder, it'll be enough. So, let's go back. So for the 2 electron case, we could kind of just do our guess. We could just do our checks. But let's look at how we could set this up for a psi antisymmetric for the 2 electron case. And again, this was unnormalized. If I wanted to have my normalization constant, I'd have a 1 over root 2 factorial. Deriving that normalization constant is a bit of a headache. I will do it after class if you're really curious. I'm going to go ahead and do 1s alpha 1, 1s alpha 2, 1s beta 1, 1s beta 2. Right? So that gives me my 2 electrons with their possibilities and their things changing, their labelings changing. And if you remember, it's going to be that minus that. Right? So if I take the determinant of this, I'm going to get my normalization factor over root 2, and I'm going to get 1s alpha 1, 1s beta 2, minus 1s beta 1, 1s alpha 2. And I can move the alpha, I can move after I have this multiplied, I can change the order of these, that doesn't matter. But having this, so I've got that negative and I've got the labels changing, all of that really matters. This gives us our antisymmetric case. Determinant of a 3 by 3 matrix. You ready? Question.
Is that 2 factorial?
So 2 factorial is equal to root 2.
Oh,
Right? It's 2 times 1.
Yeah.
So, you know, if I wrote this one out, I'd write root 6.
Yeah. Okay.
So, do you remember that? Okay, let's do a 3 by 3 matrix real quick. So I'm gonna write down. Okay, let's see if I can do this real quick. So I'm gonna write down the generic thing for an ABC matrix. So if I have a matrix that's A, B, C, D, E, F, G, H, I'm going to skip I so that way you don't think it's imaginary. So I'm just going to go G, H, J. This would be equal to A times the determinant of E, F, H, J, minus B times the determinant of D, F, G, J, plus C times the determinant of D, E, G, H. And then we'd have to do each of these. So I'd have this would be EJ minus FH. This would be DJ minus FG. And this would be dH minus EG if I also did these parts. You'll notice you end up with you're going to end up with A times this. That gives you 1, 2, 3, 4, 5, 6 functions made from these 6 functions. Some combination of these 6 functions will give us this antisymmetric case. Now, I've got some good news for you. I will not often or necessarily ever ask you to actually solve the determinant. I will ask you to set up the determinant and show that you can get the correct orientation to make an antisymmetric wave function. Furthermore, and this is the part I really like, because the Pauli exclusion idea, honestly, when I learned it, I was always a little bothered by it. And you can still be bothered by it because you're like, I don't know why it needs to be antisymmetric. Kind of explained it, a little hand wavy. But let's say we do something silly that we know is wrong, but let's say we do it anyway. Dropping the eraser. Silly, just silly. Let's say we do a 3-electron case, and I say I want it to be 1s alpha 1, 1s alpha 2, 1s alpha 3, 2s, let's change that, sorry, 1s beta, 1s beta 1, 1s beta 2, 1s beta 3. And then I say, okay, I just want to put a 3rd electron in my 1s orbital. We haven't had anything that explicitly says don't do that besides the Pauli principle. But let's see how the exclusion principle, Pauli exclusion principle, let's see how the Pauli principle makes that necessary. So I'm just going to do a 1s alpha 1, 1s alpha 2, 1s alpha 3. I'm just going to put 3 electrons in my 1s orbital. 2 of them are spin up, 1 of them spin down. If you go through and you do this, you'll find that that goes to 0. You'll find that anytime you have 2 sets of numbers that are the same, 2 columns that are the same, this determinant will end up being 0. This means anytime we've got 2 electrons with the same set of quantum numbers in our atom, we're not going to have a valid wave function. It's not going to be possible. And this is what gives rise to the actual Pauli exclusion principles from the Pauli principle, sometimes referred to as the 6th postulate. Wave functions for electrons must be antisymmetric around a single nucleus. This gets more interesting when you have 2 nuclei, 2 different positions to consider. But for a single nucleus, no 2 electrons can have the same set of quantum numbers. Otherwise, you're always going to get a determinant. You're not going to be able to find an antisymmetric wave function. So this process, not this bad one. I'm going to erase the bad one since that was just to show you that we would get a 0. But this is referred to as a Slater determinant. And it's the thing that guarantees us our antisymmetric wave function. In a class or 2, we're going to also talk about secular determinants. Don't confuse the two. They are different things. This is the Slater determinant. This gives us Slater-type wave functions. And we could generalize this to an n-electron system.
This is to avoid the determinant being fictional.
Yeah. So we can expand this to an n-electron system. So n number of electrons. Now this gets a question? No, okay. So this gets a little bit tricky because, you know, we still want to write down our different wave functions. We're going to have a 1 over square root n factorial. for our n electrons, that's going to be the normalization constant we get out. I'm thinking that would be a good like worksheet problem. And then we're going to have I look at my notes, make sure I don't get this wrong. So, and I'm going to use my more explicit labeling. I'm going to have a psi1 with an R1, a psi2. So my first column is all going to be the same wave function with the variable changing. So I'm going to have psi1 R1, psi1 R2, psi1 R3, all the way down to psi1 Rn. Or I've got n possible electrons. Now the reason I'm not just writing 1s, 2s is because then I'm going to come across, I'm going to have psi2, R1, psi3, R1, all the way out to psi n, R1. So this could be like a 1s, 1s alpha, 1s beta, 2s alpha, 2s beta, 3s alpha, 3. You know, we could use all of our hydrogen-like wave functions. There's some benefits to using the hydrogen-like wave functions. When we're using the hydrogen-like wave functions, we already know their functional form. That's going to be handy. We already know that they're orthogonal to each other. That's going to be handy. We already know that they're normalized. That's going to be handy. So using the hydrogen-like wave functions has its benefits. There's also going to be some other wave functions that have different benefits. But hydrogen-like wave functions, and these could be other wave functions, right? It doesn't have to be the hydrogen-like wave functions. Those are just a really convenient set to use. Then we're going to have psi2 R2, psi2 R3, all the way down to psi2 Rn. And you can see where this is going. It's going to go all the way until we end up with a psi n Rn. This would be our generic n-electron Slater determinant for making an antisymmetric wave function to make sure that we're following the Pauli principle. Guarantees that antisymmetry. So we could imagine doing this for pretty much any number of electrons on the periodic table, for any element on the periodic table in ionic states or non-ionic states. We can write down some number of functions that correspond to the number of electrons. We can write down the different coordinates for each electron. And this would get us some wave function. This, however, doesn't get us the answer yet. This would be the wave function, you know, just like we did before, ignoring that electron correlation term, ignoring that R1, R2 term, which is going to ruin our separation of variables. If we tried to separate variables, we'd never be able to get that R1, R2 term to split out. So let's talk about where we go from here. So this is now we're going to start talking about one of our two approximation methods. We're going to start talking about the variation of parameters method, which is a really strong method. I want to make sure I'm not forgetting anything here. So mention that. The spin orbit part we already dealt with. That's going to be a small energy correction. If you want to think about levels of energy correction, because technically the Hamiltonian I wrote down before, where I said we've got like some H1 plus H2. We could say we've got some H for the electron-electron correlation. And then we could also have some spin orbit part. This part is going to be, got to get the right number. The spin orbit part is going to be 10,000, 100,000, how many zeros is that? 5 zeros less. 100,000 times less. It's going to be on the order of 4 times 10 to the minus 5 electron volts. If you like wave numbers, it's going to be on the order of tenths of wave numbers. It's going to be, and that's for hydrogen. As you get heavier and heavier elements, this part will become bigger and bigger. But it's still going to be on the order of, you know, like If you want to think about it in terms of percents, it's going to be like 0.001%. It's going to be a small correction. The electron-electron correlation is going to be 1 to 10%. So it's going to be more important. We can't just ignore this and say we're good. The spin orbit we can kind of add in later and still say we're good. That's part of why we did it first, was to get it out of the way. Now we just have to figure out what we do. If we're ignoring this part that's really small, we have to figure out what do we do about that electron-electron correlation term. So this gets us into, if you're in the 11th edition, we're kind of jumping a little bit. We're pretty much done with, after we've done this, we're pretty much done with chapter 8. And we are jumping to chapter 9D. So we're jumping to 9D because I see how the book tries to build things up and then say, oh, and then you can, so it pretty much gives you a bunch of functions and says, all these functions, we can solve this, we can solve this, we can solve this. And then in 9D, after showing you a bunch of problems, says, this is how we solve it. I kind of like starting with, this is how we solve it, now let's look at the things we can solve. So I'm a little bit of a different order than the book, but we're jumping to 9D. If you're in the 10th ed, I think that's 10D? No. I don't remember where that is in the 10th ed. That might also be, no, it's not 9D. Oh, now I don't know which version I'm talking about. But this is the part where you're looking at variation of parameters. I'm pretty sure in 11th ed it's 9D. I'm not sure where it is. And I've got the book right here. I can even check. Yep, it's 9D in the 11th ed. I'm not sure where it is in the 10th ed. It's probably somewhere in chapter 10. It might be 10D. But let's go ahead and talk about this. So this is kind of completely changing gears a little bit. Saying, great, we can get these wave functions. These wave functions give us some place to start guessing. I want us to remember that we've got wave functions that are essentially going to be, if I'm just going back to the 2 electron case, I'm going to have some RR1, some RR2, right? So if I'm looking at 2 electron, I'm going to have an R1, R2. I'm going to have a Y, theta 1, phi 1, a Y, theta 2, phi 2. And then I'm also going to have those spin parts, psi sigma 1, psi sigma 2, which those are alphas or betas, right? I've got all of these different parts. The spin orbit coupling kind of took care of the theta phi part. And when we look at our remaining Hamiltonian, we just want to look at the radial part. So the variation of parameters essentially sets us up a way to guess a function and then find a minimized energy. And the way we're going to set this up is to first remember how we set up all of our problems. Sorry, you want to see that? Right here. There we go. I just want that there still. So we're going to set it up the same way we set up all of our problems. Regardless of how complicated our wave function is or how complicated our Hamiltonian is, it's always set up this way. H psi equals E psi. And if I wanted to calculate some average E, I would do the integral of psi star H psi. Drop my notebook. It's just one of those days. I'm going to put d tau. This could be x, y, z. This could be r theta phi. It could be 3 components, 6 components, 12, however many electrons we have. We're going to have that number of components. We're going to add an extra bit. Right? With the way we've set up our wave functions and the fact that we can kind of guess wave functions and then find figure out if our guess is good or not, we haven't guaranteed that our wave functions are normalized. So I'm going to remind us that we can always do this normalization trick, psi star psi d tau. Reminder, n squared is equal to 1 over the integral psi star psi d tau. So we can always, this guarantees normalized energies. Yeah?
The Hamiltonian and the integral operator.
Yes. Definitely. So, this is our setup. This would be our energy if we had an exact solutions. If we have an exact psi, our average energy could be many values. And it can be minimized and we can use it to get the ground state energy, right? If we're using the ground state wave function, it's going to be the average ground state energy. If we're using excited states, it's going to be the excited state energies. With the way that the variation of parameters work, essentially the key feature of the variation of parameters is that if we have any function besides the correct wave function, we're going to get an energy that's greater than the ground state. So, yeah, I'm also going to write it. So, if it's not the exact psi, then our average, I'm going to call it E phi, because that's going to be, in just a moment, I'm going to label that as our guess function. Then our E phi is guaranteed. Ooh, I think I have a typo. And I've learned that when I have typos to check them. I also find your textbook. It does all of the things that are necessary for particle in a for the ground state for variation of parameters. Never less than the true energy. So the ground state, the average ground state is always greater than or equal to. Yeah, I did have a typo. Oh. So this is, I usually don't write out all of ground state. I usually just abbreviate it GS, but when we're doing our definitional term, I thought it important. So essentially what this says is, for any not exact wave function, we're going to use some wave function phi. This is not the angular phi. This is just some other wave function. I'm trying to be consistent. Actually, your textbook just uses size as well. For some guess function, the energy of the guess function is always going to be greater than or equal to the average ground state energy. So this gives us some function. We're going to guess a function. And it's always going to give us energy that's greater than the ground state. Now you might say, well, what good is that? If we have a complicated system, for example, the electron correlation term that we can't exactly solve, we can essentially say, okay, I'm going to guess a function that I think is close to the right answer. And if I minimize that energy, I should get something that's either greater than or approximately equal to the ground state energy. The better my guess is, the closer I get to the ground state energy. So, let's see. What makes a good guess? So again, the weird thing is, we can kind of guess any function with the spin parts as well. We can kind of guess any function. We can guess anything. Anything. You want to guess? You want to guess R? Yeah, we can guess R. You can guess that it's a simple function. That probably wouldn't be a good guess because as you integrate from 0 to infinity, you're going to blow up to infinity. Right? So we want to think about what makes a good guess. So there's a couple things to think about. One thing that's kind of, some people think is very important, and some people are like, eh, as long as you get the right energy at the end, it doesn't really matter. Right? This is, if we're looking at helium, if we look at helium plus 1 electron on helium, that just looks like hydrogen. If I look at helium with 2 electrons, I can say, well, that's kind of going to look like 2 hydrogen atoms. I can guess a function like this, and that's probably going to be a good starting point for a guess. It relates to my physical system. Does it relate to the other things? 2. Kind of the core component of the variation of parameters is you need a parameter that's going to vary. You need something that you can tweak. For example, if we look at these functions, do you have your hydrogen-like wave function equations? Pull those out. Let's look at those. We can essentially insert some parameter and say, yeah, I'm going to make that thing able to vary. Now, all the r's and thetas and phi's are already terms that we're going to be working with. Those are going to be our variables. But if we look at those functions, particularly the r part, we can imagine, what if we let the charge z vary? This would be like introducing the idea of shielding. Right? I'm going to have 2 electrons. One of them is going to create some repulsion from the other that's going to make it so the attractive force is a variable. So we can look at this and say, oh, I can just make these have some variable parameter. I can say that that z is going to be turned into a z effective. And we can see what happens as I try to minimize that z effective to get my ground state energy. So having some adjustable parameter to minimize is also an important thing. This one is what pushes people away from the first two, or from the first one. So 2 is kind of necessary. 2 you have to have for the variation of parameters. Number 3 is what pushes people away from number 1. Easy math. Right? People like easy math. We'll talk about where that comes up in just a second. And the 4th is the 4th thing that we really like to have is flexible functions. That is to say, we like to have functions that aren't overly defined, that aren't like rigid and only stuck in one spot. Now, there are some times where there's benefit to having really rigidly defined functions and trying to get answers in very specific spots. But most often, we want to have like a large variability in what our function is able to do. We want to have that. We want to be able to have it shaped to what the actual minimum energy is. We don't want it to be kind of already predetermined to be a minimum that's not necessarily going to be very close to the ground state energy. So these are the things that make good guess functions. A couple things that are often used. These functions that we were already working with. Slater type functions from the Slater determinant. These usually have some beginning part. We call these Slater type orbitals, often abbreviated STO for Slater type orbitals. And they usually have some amount of junk, some polynomials, some other functions. And the big part that they have is an e to the minus AR. where that a in the exponent is going to be one of your parameters that can vary. These, who's got their equations here? These, if you look at your r, I just wanted to make sure I wasn't wrong. If you look at your radial parts, the Slater type orbitals are going to look like your radial parts. They're going to look like your radial functions. There's benefits to that. The Slater type orbitals they're already orthogonal. They're going to relate to hydrogen functions, right? So there's some easy math there. The integrals we end up with are not always the easiest. And there's a second type of really popular set of functions that people use. And there are more than just these two. I don't know why I started with that being two. Gaussian type functions, which we often call Gaussian type orbitals, GTOs. These are often something with an e to the minus AR squared. Seems like a small change, but it simplifies things a lot. Gaussian functions they're not orthogonal, but they have very easy integrals. I put very easy in quotes. Gaussian integrals are relatively easy. The main thing is, and the reason that, not the only reason, but one of the big pushes to using Gaussian type orbitals was because computers can calculate Gaussian integrals very quickly. Gaussian integrals have a very clear set of a lookup table. You can pretty much look them up and pop them out pretty quickly from a computational standpoint. So there's a lot of benefit to that. Using the Slater type orbitals, you're going to have something that has a little bit more of the problem's physicality to it. So you're going to have a little bit more relation to the hydrogen-like wave functions and relating the two things. But your integrals are going to be a little bit more involved. There's not going to be as much of a simple equation to use. You're going to have like a set of functions. So depending on what you're going for, relating to the system or easy to do in a computer, you're going to use different types of functions. So what does it actually look like when we do a problem like this? I don't have time to finish this example. Maybe I can at least start it. And I'm going to start it using the Gaussian type integrals. So we're always going to have the same set of steps that we're going to do. And it's going to be related to E phi is equal to the integral psi star h, oops, sorry, not phi star h phi d tau divided by the integral phi star phi. I'm going to solve that. So there's always going to be the same set of steps. One, solve for E phi. Two, minimize with respect to the parameter. Whether you want to call that parameter alpha or A or Z effective, there's going to be some parameter that you're going to allow in your problem that you're going to tweak. And you're going to solve, you're going to minimize with respect to that parameter. And then you're going to plug that minimized parameter back into E5 to get your minimum E5. This should give us the energy that is closest to the ground state energy. It should give us the energy that's closest to the ground state energy. Again, if we have better guess functions, we'll get closer and closer to the energy. I don't know if the textbook goes into this. I'm just checking something real quick. So, no, not so much. So, for example, a lot of this is done in computers. This is often done as a computational method because they go up to 22 parameters. That's going to give you 22 equations with 22 unknowns. But you get answers that are within like 0.1% of the right answer, or 0.01% of the right answer. So you can get these really accurate answers. And after we've confirmed that with a couple problems, it becomes reasonable to say, okay, if it works generally, we can apply this to problems where we don't actually know everything that's going on, and we can get approximate answers for that as well. Notice we're restricting ourselves to ground state energy with this method. So unless we've got some recursion relation or some way that we can find the next level energy from that, we're just working for ground state energies. There are methodologies for getting those higher states, but we're kind of restricting ourselves with this to ground state energies. So I'm going to go ahead and set up a problem, and I'm gonna say, let's say we couldn't solve hydrogen, right? This is, and your textbook. I have a beef with your textbook because it doesn't do any simple variation of parameters problem. It goes straight from saying, hey, variation of parameters is a thing, to going to a 2x2 matrix system and saying, oh, you can generalize that to a 6x6. Wow. Without really going through and talking about how this process works beforehand. So what I want to do is I want to set up a problem that's really simple, where we already know the right answer, and see how we compare. So I want to pick something that's easy to integrate. I'm going to say, pretend with me. So this is also called the variational method. Variation of parameters, variational method. So let's pretend we can't solve the hydrogen. What does the variational method give us? Well, we're going to start by defining our Hamiltonian, because that's where we always start. Negative h bar squared over 2m del squared minus z e squared over 4 pi epsilon naught 1 on r. That's our Hamiltonian. We're going to say, since we're doing hydrogen, we're going to say z is equal to 1. We're going to get rid of that z there, since we're doing hydrogen. Now we get to guess. We get to guess a function and see what kind of answer we get. And I'm going to guess a Gaussian type function, because I want integrals that are easy to do. Plus, if we guessed a Slater type function, we would get the exact answer, because that's the answer to the hydrogen atom. I want to guess something that's not the exact answer and see how it compares. So I'm going to guess. Where that A is the parameter, right? And if we look at our equation sheet, we can see that it's going to have some z, some a naught in it. It's going to have a bunch of constants inside of it, but we're guessing. And if you imagine being some of the first people to work on these problems, not knowing what the right answers are, it's kind of nice just to be able to guess a simple function. And so I'm not going to worry about the theta part, the phi part, and I'm just going to say I like this because I know it's going to crash to 0, and my Gaussian integrals aren't that hard. So in terms of guessing, this is a pretty nice guess function. Step 1, we're going to solve for E5. So this is going to be solving for two parts. We're going to have the integral to e to the minus ar squared Hamiltonian e to the minus ar squared d tau. Remembering for this, that d tau still needs to be three-dimensional space because my del is still three-dimensional space. So I'm still going to have r, theta, and phi in there. Even though my guess function doesn't have any theta or phi part, it's still three-dimensional. Divided by integral e to the minus ar squared times e to the minus ar squared d tau. Also notice, I guessed a real function. Didn't have to. I could have guessed imaginary functions, then I would still have to take the complex conjugates. I guessed real functions, so the complex conjugates are the same function back. Again, thinking about what makes things a little bit easier mathematically. We're essentially going to solve this in two parts. We're going to solve this part, and we're going to solve the other part. This part's easy to do. This is just a, well, it's not just a Gaussian integral. If we just look at this integral, the d taus are three-dimensional space, so I'm going to have a triple integral from 0 to infinity. I'm going to have e to the minus 2 ar squared, r squared, dr, d theta. Oh, well, sine theta, dr, d theta, d phi. The theta part is going to be from 0 to pi. The phi part is going to be 0 to 2 pi. So I'm still going to have my three-dimensional integral. I still need to do that part. Let's see. Where's my nice Gaussian integral? I'm gonna write down two things for you real quick. This will be handy to know. Integral of r to the 2n e to the minus a r squared. Gaussian integral with some generic code with some generic part up front. This is for even powers of r. Would be equal to 1 times 3 times 5 all the way up to 2n minus 1 divided by 2 to the n plus 1 an times pi over a 1/2. This is an integral. I want to add this integral to your equations sheet. It should already be on there. It's not, but it's a really handy integral to know. And then there's a second one that's also handy. Integral. Trying to keep things in terms of r for everybody. R to the 2n plus 1. So this would be for odd powers of r. E to the minus ar squared is equal to, this one's a little bit easier, n factorial divided by 2. 1 over a to the n plus 1. So even Gaussian integrals, odd Gaussian integrals, both of these. And the reason you don't just get zeros is because they're integrated from 0 to infinity. Even integrals, odd integrals, for the Gaussian type integrals are going to have those types of solutions. That means this thing's not that bad to solve, right? I know my sine theta. Hopefully we all recognize that the sine theta, d theta, d phi part, with that and that, that's going to give us a 4 pi. We're going to get 2 pi from the phi part, and then a factor of 2 from the pi part, from the theta part. Is everyone okay with that? All of that's just going to give me 4 pi. Okay? Okay. So then the only part that we actually have to solve is this other part, which we just found, which we just were given integrals. We were just given the answers to. So that part, make sure I've got the same thing. Okay. Oh. Oh, yeah, okay, that's why that happens. I was like, wait, the power of something disappears. This is going to give us, so in this case, r is equal to 2. That would be using this integral, where n equals 1. So I'm going to have 2 minus 1. I'm going to give myself more space. Let's do it over here. 1 for that part divided by 2 to the power of 2. Our parameter a to the power of 1 times a pi over a to the 1/2. That's that whole integral. I can erase to the power of 1. That's kind of silly. I'm going to turn 2 to the power of 2 just into 4. Because that's 4. And that's going to give us a way where we can kind of simplify things. If I bring in the 4 pi, notice the 4 cancels out. I can bring the a in. I can bring the pi in. Did I miss a power of 2? I might have missed a power of 2. This will give us, for our bottom part of the integral, this will give us a, if I bring the pi in, I'm going to get a pi cubed to the 1/2. I bring the a in, that's going to give me an a cubed to the 1/2. Or if I want to write that a little bit differently, pi over a to the 3/2. Right, so if I bring the a squared times a would give me the a cubed on bottom. And then this pi is from here, I would multiply by this. So that pi times that, bringing this pi in, would give me pi cubed to the 1/2. Okay? So this gives us the bottom part, and I'm vexed because I have an extra factor of 2 in here someplace. So I got to double check that. But this is going to give us this bottom part. This is essentially our normalization factor. We've done the normalization part. Now we have to do the really fun part. Right? So now we have to do this top part, which I'm going to do right here. And I'm going to set it up. We don't have time to finish it, but we're going to set it up. So this top part, keeping in mind that I've got my Hamiltonian. I'm going to do it in black. So now I'm going to solve this part. Or at least I'm going to set up that part. So I'm going to have, again, another triple integral. Again, because there's no angular part in my guess function, the sine theta part, the sine theta, d theta, d phi is just going to give me a 4 pi. I can kind of just shuffle that part away. I'm going to have an e to the minus ar squared times negative h bar squared over 2m del squared minus e squared over 4 pi epsilon naught 1 over r operating on e to the minus ar squared sine theta dr d theta d phi. And I want to point something out that's really important here. When this operates, it operates on the ar squared. It doesn't operate on the volume element. It's just operating on the wave function, not the volume element. So make sure when you're setting this up, you're paying attention to that. Okay. So this term's easy, right? That term, this first term, or sorry, the second term is easy because there's no derivatives or anything. Second term's actually, the first term's not actually as bad as it looks because we've only got radial parts. We don't have an angular part. So when I look at my del squared here, I really just have to look at the radial part of it. I really just have to look at the 1 over r squared d by dr, r squared d by dr. That's the only part I really need to look at. And if I just do that del squared on my e to the minus ar squared, assuming I didn't make any mistakes, you're going to take the derivative of e to the ar squared. That's going to give you an ar. That's going to give you a 2ar. You're going to multiply by ar squared. Chain rule. Bring it down. We'll do this next time as well when we're starting out. You're going to get a 4a squared r squared minus 6a e to the minus ar squared. And this is where we'll pick up next time doing that derivative. Actually, do that derivative just as for fun in the next 48 hours. Do that derivative for fun. And then we'll see how we can get to solving for E phi and then minimizing to give us a legitimate example of what we do with variation of parameters, because we're going to extend variation of parameters very quickly to n by n systems. So having at least one concrete example we can look at will be nice. So do that derivative, prove that that's true, and then plug everything back in. Also, if you can, see if I'm wrong. I think I'm supposed to have another factor of a 1/2 here that I dropped someplace. So also see if you can find that typo. I'll see if I can find it as well. And that's what we'll pick up next time. Any questions before you get to... Yes, question.
We're gonna talk about the schedule.
Oh, right. Let me go ahead and stop the video so we can talk about that.